Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully, you guys are doing great. Had a good, extra long weekend. I also had a good weekend, which I'll tell you guys about later, especially a good Valentine's Day. Don't worry, I don't kiss and tell. It's not that. But I guess I should start with the bad news because, there's always bad news. Migraines flaring up today, so I'm not really at 100%. I think we'll survive, but I'm not feeling great, which will kind of explain why I probably won't seem as jovial about the good news as I really am, because I am. I'm over the moon about it. But on Valentine's Day, my brother had his first kid, so you guys can call me Uncle Jhevon from now on. Yeah, the syllabus will be amended. Very excited about that, so that's great. Even though I probably don't seem as excited because my headache is like at a level 7 or 8 right now. But yeah, that's good news. So I don't know, maybe I should look good for the thumbnail, look excited or something. But yeah, let's actually get into it though, because we all gathered here for a special reason. Let's see, do I remember what we're doing today? I do. Okay, all right, let's jump into it. And it all starts with story time. So we're going to talk about baby Gauss. And adding the first 1,000 numbers. So, legend has it, I don't know if this is true, but people have always said it was true, at least in math circles, okay? So, there's a famous mathematician called Carl Friedrich Gauss, German mathematician, very prolific, very important guy, very smart guy, responsible for a lot of the math that we know today, especially in complex analysis and a lot of applied math. Okay, so legend has it, when he was a kid and he was in class, this is when he was very, very young, 4 or 5 years old. So, in class, they're learning how to count stuff with stones and things like that. So one day his class was being rowdy and the teacher was getting really upset and she was like, everybody sit down, be quiet. Here, I want you guys to add all the numbers from 1 to 1,000, right? Now, these are kids, they barely know how to count on their fingers at this point. So she thinks, all right, that's going to keep them busy for like the rest of the year, right? So everyone's like, oh, I gotta start adding all the numbers from 1 to 1,000. I don't even know if most of the kids knew how to count to 1,000 at this point. So then, like 5 minutes later, Gauss comes up and gives her the answer. Oh, it's 50,050. And then he just goes about his business. Little Gauss was very versed in arithmetic and algebra at this point. Now, how did he did this so quickly? Because I mean, even if he could count to 1,000, it should take you longer to add all the numbers from 1 to 1,000. We're talking about all the whole numbers. So here's what little baby Gauss noticed. So he's like, okay, being very good at abstract thinking, of course. He's like, okay, here's what I want to find. Right, and he just wrote down a few of the numbers. Let's write down the last 3. 998, 999, and 1,000. So he already knew about commutativity of addition. So he's like, okay, this is the number I want to find, but that's actually the same as if the number were written the opposite way. Now, here's what he also noticed. If I were to add both of these lines, what would happen? I would get 1,001 here. Interesting, I get 1,001 again here. Oh, look at that. That's 1,001 there too. That's 1,001. That's 1,001. Oh, and that's 1,001, right? Now, adding these 2 lines actually gave me double the answer that I wanted, right? So then he was like, okay, so it's 1,000 numbers. This is 1,000 and ones, and this is double what I wanted. So that means the sum I wanted is 1,000 times 1,001 divided by 2. You divide the 2 into that guy, that goes 500, and yeah, that gives you 500, 500. 500,500, right? So that's how you add all the numbers from 1,001 Gauss style. So yeah, now it turns out this is a very neat trick, and it's something that we can do quite generally. Now there's something called, to bring it back to high school, a geometric series. So named, I believe, because of its connection to the geometric mean. And it's a series of numbers that have this particular form. It's like you have some value, and then what you do is you multiply that value by some number called r. You multiply it by some number r again. You multiply it by some number r again. You multiply it by some number r again. And you keep doing this for a certain number of times until you have n of these numbers. So ar to the n minus 1. Okay. And the series, this is called a geometric sequence, but the series comes from being able to add it up. Now, you may notice that this actually looks very similar to some that we've seen before, namely compound interest. Remember when we were raising that initial $1,000 that we deposited into account, then we realize it gets multiplied by 1 plus r over n, and then after another cycle, it gets multiplied by 1 plus r over n again, then 1 plus r over n, 1 plus r over n, 1 plus r over n. So that raised it to the nth power, and then in 1 year, you get multiplied by that thing n times, and then we put t there to proliferate this over years, right? So it's the same pattern. You actually get a geometric sequence by doing that. Now, here's the thing. What if I wanted to add up all those numbers, which in today's class, you're going to see why I would like to do that? Well, we can use like Baby Gauss's trick. We can call this something, and then it turns out we're going to actually do it slightly different. We're going to multiply that thing by r. So a times r, of course, you get ar. A times ar times r, you get ar squared. I'm just shifting it, so maybe I'll not shift it. You get that, right? Now that's r times what you want. But what you'll notice now is that you've actually reproduced a lot of the original series. In fact, your ar to the n minus 1 is the second to last guy in this. And so here's what we can do. We can actually subtract one line from the other. So if I call this line 1, call that line 2, what I'm going to do is I'm going to take line 1 and subtract line 2. And what you're going to notice happening is that these guys are going to cancel. Of course, there's going to be a minus 1 times this guy because you're subtracting. And so it turns out this side is going to become a minus ar to the n. And then this part here, you're going to have s minus rs. In other words, you're going to have s times 1 minus r. And so adding up all those numbers gives you this guy, which we can write as this. And this gives you, I'm not going to box it. I mean, it's a nice fact, but it's not one you have to remember, really. So this is the sum of a geometric series. right? Which is a cool thing, which has a cool story to lead into it. Now, why did I tell you that story? It's because I actually want to do some mathy stuff today. Most of it you're not going to have to know, so don't worry. But I do want to just motivate one of the formulas that we're going to be working with, just for you to see how some of the workings happen, which is the main formula for section 3.3. The formula for 3.4 is similarly derived. I think we'll deal with that tomorrow, but I'm not going to go as detailed there. I'm just going to basically tell you guys the formula. But this idea is going to be important. We're going to use this. We'll use this later. But yeah, to be fair, just so everyone's aware, I'm not going to like test you on being able to do this trick, so you don't have to freak out about this. I just think it's something interesting that I should tell you guys about, and kind of motivate where we're going. So yeah, it's actually story time. Like, you don't have to take this too seriously. Yeah, so we have that. Now you're going to see what I'm going to do with that in a bit. At this point, probably should review what we have done. So last time we were talking about, more about interest rates. We really started to see the difference between simple interest and compounded interest, which is very, very important, because the first day we spoke about this, you probably didn't notice much difference between the two, but I wanted to show you that there is a clear difference between the two. And we're going to see more of that later on. So we already knew the formula for simple interest and compounded interest, and we did a couple calculations. I introduced continuously compounded interest. That gave us a new formula. Then we did some examples with that new formula for some comparison. Told you about the idea of an APY, which is a way to kind of normalize, is what you would normalize? Maybe. Normalize is kind of what a math person would call it. It's when you're given various interest rates computed various ways, and you kind of want to compare the two. The idea is to translate everyone to their equivalent simple interest calculation. That way it's more intuitive, and that is the point of APY. We developed formulas for that, and so we could actually compare interest rates better. And yeah, that's pretty much where we ended. But the idea is the following, as you guys may have noticed. Everything that we've been doing up until this point, essentially what we do is we have a principal, we put it in an account, and then we just wait, right? Which in real life is not very realistic. So we kind of want to make things a little bit more realistic, because people don't just deposit money into a bank account once and then never do anything again, right? People do stuff. They continually deposit. Maybe every month their paycheck goes into a bank account. So the idea that we want to now deal with is the idea of repeated payments, right? So it's not just, oh, I put $1,000 in the bank. It's, I put $1,000 every month into the bank, right? And then I want to know, how is my money adding up? Which now you kind of get why I'm telling you about adding up a geometric series, right? So your money's being compounded, so it looks like the P1 plus R to the N, and then we're adding that kind of thing to itself over and over. And then we want to add up after a certain amount of time. What should that thing look like? How much money should I have in that scenario? So I'm depositing $1,000, but at the same time, the balance in my account is growing compound, right? So how do we actually model that situation mathematically? So this leads into what we really want to talk about today. Modeling what we've done with repeated payments, right? So if we keep putting money in the bank, how does it grow? How do we do that? We had a formula for if we just put a lump sum in the bank and left it alone, right? And this leads to the idea of future value of annuities. And closely connected, something called a sinking fund. We're going to learn about that today. Maybe might spill in a little bit into tomorrow, right? So now it's serious. Now it's go time. So you should start paying attention and taking notes and stuff like that. So let's actually talk about what this is. So let's define what an annuity is. An annuity is a sequence of regular payments. Regular in the sense that something is repeatable about it. You can predict it, like regular meaning every month, time-wise. Right? So it's payments that are coming in ever so often, every month, every week, every something, right? If all payments are equal, and there's a very special type of annuity we'll be interested in. Not because it's the only one around, but it's the simplest version that we are covering in this class. And interest is added at the end of each pay period. It is called an ordinary annuity. So this is the typical type of annuity. This is when you're making repeated payments. They're all of the same size. You're making them at regular in time intervals, and interest is added at the end. So even if you deposit money into the account at the beginning of the month, the bank will add your interest at the end of the month. They always add it at the end of the month, at the end of the period. Okay, so in this class, we'll only consider ordinary annuities. So for us, whenever you hear me say annuity, I'm talking about an ordinary annuity. Right? There are other kinds out there. Okay, so that's just something to note. Okay, but that's what annuity is, a sequence of regular payments. Of course, we're going to want to be able to do some math with these regular payments. Okay, so let's actually develop what we want to be able to do. So suppose the size of our regular payments is R, right? Now, that's not usually the variable that's used, but I just want to cut down on writing. I'll tell you the actual variable that's used afterwards. It's like a 3-letter variable, so it's very weird. It's going to be annoying. The interest rate is little r, and n equals number of times compounded. So this means m is the number of periods, which is going to be n times t. Okay, so here's what we're looking at. So here's a time interval. So this is now, right? You put in, say, R dollars into the bank. which means at the end of period 1, well, in period 1, sorry, in period 1, you have R dollars, right? And then in period 2, you also deposit R dollars, and so on. And this keeps going on. Dot, dot, dot. Let's suppose you do this for M periods, right? So the number of months times the number of years you're doing this for adds up to M. So this period M minus 1, you put in R dollars, and then in period M, you put in R dollars again. Now what we're going to do is we're going to calculate so these are your payments. What we're going to calculate now is the future value. Okay. So what is the R dollars that I put into the account now going to be worth at the end of this period that I'm talking about? Well, it gets hit starting with the next period. So this R here, the first R, this guy, he's going to get hit with interest. So he's going to become 1 plus R over N. And how many times would he actually get hit with interest? Well, since he starts getting hit with interest starting at the second period and they're M periods, he's going to get hit with interest one less period, right? There's going to be M minus 1 times that I'm hitting this guy with interest, and I'm going to be multiplying by 1 plus R over N. Similarly, this guy here, he's going to get hit with interest M minus 2 times. This guy here, he's going to get hit with interest N minus 3 times. And this pattern continues. This guy here that was given, you paid in the second to last period, he only gets hit with interest once, right? So he gets hit with interest, so that's a 1. He gets hit with interest 1 time at the end of the M minus 1 period. He doesn't get hit with interest again. The last amount that you put in, it stays like that for the purpose of this, because we would add interest at the end. So that guy doesn't get hit with interest until the M plus first period, right? So this is all the money that you've accrued. So the sum of the future value is going to be equal to, now I'm going to write this around the other way. So it's big R to the 1 plus big R times 1 plus R over N plus big R times 1 plus R over N squared plus, and it keeps going up to big R times 1 plus R over N to the M minus 2 plus big R times 1 plus R over N to the M minus 1. Now what you're going to notice is that looks a lot like, in fact it is, a geometric series. It's this guy, right? If I swapped out my little a with big R, and I swapped out my little r with 1 plus R over N, you get exactly this, right? So, gasp. This is a geometric series. Which means, what does my future value add up to? Well, it's A times 1 minus the 1 plus R over N to the M all over 1 plus all over 1 minus 1 plus R over N. Now, of course, in the bottom, we can clean that up a little bit, the 1 minus the 1. And then with this negative, I can turn this around. Let's write it with a negative first. And having that negative is kind of weird. So what I would do is I would multiply the entire thing by a negative. Multiply by -1 over -1, I would get 1 plus r over n to the m minus 1 all over r over n. Now, if any of you have taken a finance course, this should start looking very familiar to you. This is actually the formula for the future value of an annuity. And so changing notation. Because usually we call R PMT, at least in a lot of like accounting books and finance books, you'll see them call R that. And we'll change our M back to N times T. And so we get FV equals PMT 1 plus R over N to the NT minus 1 all over R over N. And this is the first formula that you need to remember, which is a monstrosity. And it's probably hard to remember. So I kind of told you how to kind of build it up. But at some point, you're going to have to know this. We're going to use this all the time. And yeah, this is the formula for future value of annuities. Very important. Main formula for section 3.3, which is where we are now. Maybe I should put that in. That might be useful. So this is section 3.3. So we're in chapter 3, section 3, and this is the main formula of section 3.3, future value of annuities. It turns out we can actually solve for it the other way. We can make PMT the subject of the formula. To get PMT equals FV times R over N, and then you would divide by the 1 plus R over N to the NT minus 1. And I'll check I'm writing this down correctly. The formula in 3.4 is very similar, except that there's a negative power and then something is turned around. I always sometimes my hand writes the other one. And this one is called the sinking fund formula. We'll discuss later. But the future value of annuities formula and the sinking fund formula, they're the same formula. It's just depending on who you want to solve for. It's called one thing over the other. Yeah, so that's that. Yeah, so that's what story time was about, me motivating this. Now, like I said, you don't have to know how to get this, but I thought I would just kind of show you how this weird formula came to be. And yeah, changing the subject of the formula, we get what's called the sinking fund formula. And this is our new formula. So let's actually play around with it. I think I hope I did, if I'm remembering correctly. Yes, I typed up some examples that we're going to do. And the first one, the first example, I think, if I remember correctly, we're going to get a lot of mileage out of this one. There are a lot of things we're going to be able to learn just by really kind of getting into this example. Okay, so here's our example, and here's the formula. I mean, for now, you might want to take a screenshot of it in case we have to use it. Okay. So here's the example. Okay. You deposit $1,000 per month, which is more realistic. No one just hey, bank, here's $1,000, and you never see them again. Every month you come back, you deposit $1,000. Maybe you get your paycheck and you deposit $1,000 religiously, right? Into an account. Now it's being compounded 4% APR, right? So remember, the real interest is going to be a little higher, but I don't think we have to worry about that for this problem. How much money would you have after 40 years, right? So let's say you're very diligent, you're working hard, you keep your head down, you're not like loose with your money, at least not with all of it. You know, you have some play money to play with, but you religiously $1,000 a month, every month for 40 years, you keep this up. And, you know, that's your money that you put in your savings, right? How much would you have at the end of 40 years? That's, you don't want to actually plug that into your calculator. And I mean, you could like do a drag and drop thing in Excel, but even that's kind of weird to actually do that. Even in Excel, they would have you use, by the way, if you try to plug in of code into Excel to do this, to calculate this, Excel actually uses this formula, even though you won't have to know that as a human being, but you should. So let's actually see, how much would we have at the end of a 40 years? Well, here, a bigger. So let's see. You keep this up for 40 years, right? Your entire working life. Okay. Just $1,000 a month, which depending on, I mean, you guys should be able to get that depending, you know, you get a business degree from Fordham. Not out of the question for you guys to be able to do this and still be able to live your life reasonably comfortably, at least after a while, you know, a couple years out of college. So let's see, you can get 4% APR, which is not totally unrealistic. This is a very realistic example. Let's see. So your payments here is 1,000, right? So here, payment is 1,000. What else do we know? R is 0.04. What else do we know? N is 12, right? Because we're assuming that this is an annuity. So you're getting hit with interest at the end of every pay period, which is at the end of every month. So it's being compounded 12 times. And they told us compounded monthly also. And what are we doing? T equals 40. Do we need to know anything else for that formula? I don't think so. I think that's it. So this means that in the future, 40 years in the future, what is the future value of my account? Well, it's going to be whatever my payment is times 1 plus R over N to the NT minus 1 all over R over N. So that's going to be 1,000. And I'm going to ask you guys to plug this into your calculator to make sure you know how to use your calculator. And make sure you know how to, where you need all the parentheses. N is going to be 12 times 40, I think it's 480. So actually you're getting 480 pay periods here, and you're adding interest at the end of each of these periods. 0.04 over 12. Now someone tell me what value that is. In fact, in this section, I think I only actually want to do 2 examples. That's going to give you everything. But I'll probably save the other one for tomorrow. I'll leave it in the notes so you guys can try it for tomorrow if you want. But I'm going to kind of want to elaborate on this example. So we're going to spend the rest of our time here. Yeah. So what do we get?
I plugged it in and I
Yeah.
hope it's right. I got 1,400,000. No, 1,481,661.3.
Does everyone agree?
I got something different, but it's close.
What did you get?
I got 1,181,961.3.
Yeah. Give me 2 decimal places. It's numbers, so we want cents.
34.
Okay. So that's what I got. So because it's 2 of us, I'm going to go with that number. So
okay.
So if you didn't get that number, you should be aware that you plugged in something in your calculator. Maybe you don't know how to use the parentheses or something, but I believe the number that you should get, since 2 of us have gotten it so far, is that. Yeah, it's over $1 million. And that's actually quite realistic, right? $1,000 a month for 40 years, you'd be a millionaire by the time you retire. Okay. At least. The stock market actually returns more than that. And so depending on how smart you are with your taxes, don't do anything illegal, but if you're smart to pay the least amount of taxes as you could, and you lose the least amount of money as you can, you'll actually get more than that. Okay, so yeah, you'd be a millionaire in 40 years just by doing this. Automatically have $1,000 debited from your checking account every month. Just forget about it. Do whatever else you want to do. And even if everything else goes wrong in your life, at least at the end you end up a millionaire. You know what I mean? It's not a bad deal. Now here's something that's interesting. So the follow-up question is, how much of this final sum is from interest? Here's what's interesting about interest. Okay, all right, no more. Right? How much of that is from interest? How would you figure that out? Like if I were to ask you, okay, how do we get to the interest? What would you say? How are you going to do it?
The amount minus.
Yeah, the total amount minus.
The cost.
Okay, so I think by cost you mean what it costs us to do that. So it's like the sum of all payments, right?
Yeah.
So take what you actually put into the account, subtract it from this value that we got, and the rest of it is interest. So there's some that you actually put in, and the rest of it grew by interest. Okay, so the total is 1,181,961.34 minus, how much money did we actually put in? How would you compute that?
$1,000 times 12 times 40.
Right, $1,000 times 12. So that's that's $1,000 times 12. That tells you how many times in a year, and then you multiply by 40 because it's 40 years. Yeah, exactly. So 1,000 times 12 times 40. Let's actually, what is that, by the way?
480,000.
480,000. So over this time span, you would have actually put in 480,000. Now, if you subtract those, and you guys can check my math here, that's 760,691. $701,691 is interest. Okay, so now I want to bring something to your attention here. What do you notice about that number? Anything jump out at you at that number? Like looking at these calculations, anything jump out at you?
It's more than the money that you put
It's
in.
more than what you put in. The compound interest, and again, this is me showing you guys the miracle of compound interest. The interest would be more than you actually put in, right? This is what it means to get your money to work for you. This is when people say that, this is what they're talking about. Like, it's like your $480,000 went to work to make money and it made more money than you did because it's growing compounded. Whereas a human being, you're not going to improve compounded over a year. You're not going to get 10%, become a 10% better person every year. It's not going to happen, but your money can do it, right? So it's more than you put in. Right? That's the math. Like, and this is what I was trying to tell you guys a couple of classes ago, where it's like all these billionaires, how they're giving away all this money, and then somehow they're richer the next year. It's the compound interest that's doing the extra work, the heavy lifting, right? So the interest on what you're doing when it's compounded is going to end up more than you put in, right? Almost double what you put in, right? So yeah, there's that. Now, here's something else I want to do. So yeah, this is the main question here, but there's something else interesting that I wanted to point out to you. Let's say, repeat the above. Same numbers, everything except one place. With 2% APR. Now, there is a method to the madness. There's a reason why I'm choosing these numbers, which I'm going to get at soon, but let's just actually do the calculation. So again, our future value is going to be, we write down the formula all the time until we remember it. Myself included. I actually don't use this formula a lot in what I'm doing. I'm not mostly into finance. So the payments, it's still 1,000. The interest rate this time is what changed. To the end, still 12 times per year for 40 years. Nothing else is changing there. I'm just changing the interest rate, nothing else. Now, especially the person who got the wrong answer first, can you tell me what the answer is now for this one? Let's see if you can get the parentheses correctly this time. Tell me what you got here. Then I'll comment on the answer for a couple of minutes, more like a rant, and then I'll let you guys go. And I would leave. Oh, I actually typed out. I typed that out. Maybe I should do that. And the other example I want to do is the sinking fund example, but we'll do that tomorrow to start off. I'd recommend that you kind of try to do it before I do it tomorrow, just to see if you'd understand how to use it. So maybe move this guy here. In the above example, suppose the APR was 2%, how much would you have over 40 years? And then discuss, which is pretty much Jhevon ranting for a couple minutes. What did you get?
734,435.6247. So it just rounds to
Yep.
0.62.
Yeah. Congratulations. That's what I got. So two of us got that. 734, 435.62. Look at what a difference a drop in 2% makes. You were a millionaire. Now you're not. Now, of course, this is compounded 2%. So this is growing a heck of a lot more than your checking account would. In fact, your checking account would give you this value here. So someone saving their money for a rainy day in a checking account, they're coming out at the end with 480,000. Someone who knows about compound interest because they paid attention in class would come out with $1 million. They'd come out a millionaire, of which most of that money's from interest, had nothing to do with what they were doing. Now, if they got 2% less, they still did better than 480,000 by a long shot, but not nearly as well as they could have done. They would have ended up with 700,000 there. Now, here's something I want you to note. If I took the 734, 435, 62 divided by the original amount, this gives you around 62.14%, right? So the interest rate dropped by 50%, but your gains dropped by more than 60%. Again, that's compound interest. The same way compound interest can help you, it can also hurt you when you're not using it correctly. Example, credit card debt, example, right? Now, these numbers are, oh, and also, I should also mention, this means at 2% APR, when I kind of normalize to get rid of the money that you actually put in, you gained 1/3 of the interest on your money. And I would like you guys to know something. Fact, as of 2015, so not that long ago, it's probably around the same now. It might actually be a little lower, but this is a good ballpark. Average fees for money management is around 2.74%. So growing at 2% wasn't just a random number I picked out. This is roughly going to be about how much someone charges you to manage your money. And that's on the lighter side. If you're with like some fancy hedge fund, they'll charge you a lot more, by the way. But average retail investor, guy just investing for retirement, has someone manage his money, like a fund or something, some financial firm. Roughly, when you add up all the fees, it's going to take about 2%. So 4% is a very modest gain. You can definitely get that relatively easily. If you're not getting 4% on your money, you're doing something wrong. You should really be getting closer to 8, 9 before taxes, right? So 4%, very modest. Now, what I did was I decreased that percentage by 2%. Why did I do that? Well, because the average fees to have someone else deal with your money is 2%-ish. What are the results of this, right? So this is what I'm trying to get at. Because a lot of people feel like either math is not important or they'll just hire someone else to do the math for them. I want you to understand what that decision means, okay? You could have made 4%. You hire someone to manage your money, and what they did was they come to you and they say, I'll charge you a 2% fee to manage your money. Now, here's the first thing. To a lot of people, that does not sound like a lot of money. Oh, I'll give you $100. You're going to make me rich, and all I have to do is pay you $2 out of that $100. That sounds like a great deal. Sign me up. Now, here's what would happen if you signed that contract, right? You are going to make $700,000, right? a third of the gains that you would have made had you done this by yourself. On top of that, notice that money didn't just vanish into thin air. Who got that extra 2%? Who got the rest of the gains? The actual person who charged you the 2%. See, that person who charged you the 2% actually made 2/3 of the gains that you would have made. They actually made more money off the deal than you did. So that 2% was not a little bit of money, right? But however, because compound interest messes with the brain, it's not very intuitive. You don't even realize, right? If you're paying more than 1% in fees for someone to manage your money, you are getting robbed, chances are. Unless they really are like a Warren Buffett or they're like an Oracle or something. Chances are you're getting the bad end of that deal. You're literally giving away 2/3 of what you could have gained to someone who's taking no risk. They're taking your money. You're putting up all the capital, right? So it might not, a 2% decrease might not seem like a lot, but again, compound interest is weird. You actually lost out 66% of what you could have made. And that actually goes to the person that you're paying to manage your money. And this is assuming they're not embezzling from you. This is above board, right? Them following the law gives them 2/3 of your gains, right? And so, yeah, a 2% fee is actually very expensive. And you want to think of it as that expensive. So a lot of times, I don't know how many of you are into Shark Tank. And sometimes you'll see the sharks do something like, you know what, I'll give you X amount of money for 8% equity or whatever. And then the person goes like, I'll take the deal for 8.25%. And a lot of people watching that are like, what the hell is he fighting for 0.25% for? It adds up, dude. Look at this. Look at what 2% can do, right? 0.25% of millions. Come on. It's actually a lot of money that they're fighting for. So sometimes you'll hear these finance jargons and people are like arguing about 2% and 0.25%. And you're like, why are they making such a big deal about this? Compound interest is why they're making such a big deal about this. Like that 2% over 40 years compounded adds up to a hefty chunk of change. And we are talking about gaining more money than you even invested in the first place, right? This is what I'm talking about. It's very important that you understand this compound interest stuff. And it's very important that you understand that the numbers, while they might seem small to you now, they actually have a big impact in the future. And you need to know how to do the calculations. And you need to know. Now, I'm not saying don't hire a money manager. You should. You should actually get financial advice from experts. Don't think that that's what I'm saying. But you should know what you're signing up for. You go to a financial advisor and they say 2%. You should know what that means. And you should ask yourself, is this person worth paying that? Right? You should know what you're getting into. And a lot of people just don't, because the numbers just don't make sense on a large time scale when you're compounded. And yeah, we are going to wrap up right there. So hopefully that was interesting. Hopefully you guys like story time. We'll stop there. We'll pick up tomorrow. I will leave the example of sinking fund in there. And sinking fund is basically solving for the payment instead of the future value. So try to read that example, see what you can come up with. We'll start that tomorrow, and we'll actually start section 3.4 tomorrow as well. And that's talking about present value of annuities. Have a good rest of your day. We're going to wrap up there. I have another section of this class in like 2 minutes, so I'm going to go. Hopefully everything's good with you guys, and I'll see you guys in the next one. Ciao.